This is Math 131, section 5.4. We're going to start by talking about the Pythagorean theorem. Okay, and Pythagoras was a Greek mathematician, and he was saying that in any right triangle, that is a triangle where you have a right angle or a 90-degree angle on one side, one angle. Okay, the square of the length of one side added to the square of the length of the other side equals the square of the length of the hypotenuse. You may remember this as a squared plus b squared equals c squared. Okay, so the two sides we're talking about where we square and add are the sides that form that right angle. So a squared plus b squared equals the hypotenuse is the angle opposite that right angle, and c squared. And you can think of this right triangle as half a rectangle. You know, we're kind of cutting a rectangle in half diagonally, and the hypotenuse is the cut. Okay. So that formula that we call that our Pythagorean theorem, okay, and basically says a squared plus b squared equals c squared. Okay. And the hypotenuse is always the longest side of that right triangle. Okay. Okay, now we're going to talk about irrational numbers. Okay. We talked about rational numbers before, which was ratios of integers, fraction of integers. Now irrational numbers, it's a real number. That means it's a number that measures a quantity that cannot be written as a ratio of two integers. Okay, so we can't write it as a fraction of two integers. Okay, so when we look at irrational numbers, we're going to notice something. The decimal goes on forever, dot, 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 and there's no pattern to it. Okay, there's no repeating pattern. Okay, so we can say the decimal just keeps going and it doesn't have a repeating pattern. Okay. There's some patterns in these numbers, but they're not repeating patterns. They're you know, it's not a repeating pattern here, but you can think of like the decimals just keep going in sort of like a random fashion. Okay, irrational numbers. Okay, let's talk about radicals or roots. Okay, that root symbol is called the radical sign. Okay, the number inside the radical sign is called the radicand. Okay. So if we take a square root, we just say take the square root of 4, right? We'll look at that example to start with. Square root of 4 is 2. Okay. Now what we're doing with square root is we're trying to see a number that squares to get 4. Okay, a number we can multiply twice to get 4. That's so the radicand here is 4, and we're taking the square root of 4 to get 2. Okay, we talk about principal square root. We're talking about positive square root of a number, n, okay? And we can write that as square root of n, okay? It's the positive number that when multiplied by itself gives n, okay? So for example, for square root of 9, we're going to say 3 but not minus 3, even though minus 3 times minus 3 does give us 9. And for square root of 36, we're going to say it's 6. Not minus 6, even though minus 6 times minus 6 gives us 36. So when we talk about a square root, we're going to talk about just the principal square root, which is the positive one. Okay, so we're only going to use the positive. So square root of 9 is 3, not minus 3. Square root of 36 is 6, not minus 6. Okay, that means we're using the principal square root. Okay, let's talk about numbers that are perfect squares. Perfect squares are numbers that where you take a number and square it and you get this number. So 1, because 1 times 1 is 1. 4, because 2 times 2 is 4. 9, because 3 times 3 is 9. 16, because 4 times 4 is 16. 25, because 5 times 5 is 25. 36. So we can actually do our square roots, you know, writing those out. So the square root of 1 is 1. The square root of 4 is 2. Okay. Square root of 9 is 3. Square root of 16 is 4. Square root of 25 is 5. See our perfect squares, we're squaring 1 to get 1, 2 to get 4, 3 to get 9, 4 to get 16, 5 to get 25, and then finally the square root of 36 is 6. So see, we can, if we take square roots of perfect squares, we're going to get a number, a whole number, okay, a positive number, right? So that these perfect squares are perfect square roots. We can take a radical and multiply it by a number. So a number that multiplies times a radical is called the radical's coefficient. Okay, so let's say we have this. This is the same as writing this as 3 times the square root of 5. Okay, so that's a dot for times. But basically we're saying when you have that 3 in front of the square root of 5, that says we're taking 3 times the square root of 5. And that 3 is called our coefficient. It's the number part in front. Okay, and you can kind of think of it like this. Well, I have square root of 5, and I have 3 of those. Okay, that says we have 3 of these. Okay, now we'll look at the product rule for radicals. Product rule for radicals says this. If you're multiplying two things inside a radical, inside a square root, then you can break them out separately. So square root of a times b is square root of a times square root of b. Okay, that's if a is positive or 0 and b is positive or 0. So they can't be negative, and we're not going to worry about negative square roots in this course anyway. So, but you can break out those. Now this is not true. We have to be careful. Okay, square root of a plus b is not equal to square root of a plus square root of b. So we cannot break them out if we're adding. We can only break them out separately if we're multiplying. Okay, now we're going to talk about simplifying radicals. When we simplify a radical, we're writing the radical as a product of two radicals. Okay. One of the radicals should contain the greatest perfect square that is a factor of the radicand. Okay. Then simplify the radical containing the perfect square factor. In other words, we want to take the perfect squares out of our radicand that divide out and simplify them. Okay. So for our first example, let's look at the square root of 18. Okay. Now, what we're looking for is our perfect squares. Remember, our perfect squares are, 1 squared is 1. We won't do that one. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. And we're looking for the highest perfect square that we can divide out of this. Now, we see 4 doesn't go into that, but 9 does. So 9 goes into 18 2 times. So we can write this as 9 times 2 instead of 18. And then our product of radicals, remember, we can separate them out, right? So we can say square root of 9 times square root of 2. Well, square root of 9 is just 3, right? It's a perfect square. So we have 3 times the square root of 2, which you can write with a dot or just put it in front of it, square root of 2, and that means times. Okay, 80. 16 goes into 85 times. Okay, 16 times 5 is 80, so we can break that out into the square root of 16 times 5, which is square root of 16 times the square root of 5, which is just 4 times the square root of 5, because our square root of 16 is 4, and we just put the 4 in front of the square root of 5. Okay, let's talk about addition and subtraction of radicals. Okay, if we have the same radicand, like square root of 5 or square root of 3, and we have the same, to add or subtract 2 or more square roots, okay, with the same radicand, just add or subtract their coefficients. Okay, and the answer is the sum or difference of the coefficients multiplied by the common radical. Okay, so let's see what that means. Okay, so let's start with this. 5 times the square root of 3 minus square root of 12. Now we can't combine these because they're not the same radical, right? These are not considered like radicals. They're not the same, right? But we can take our square root of 12 and write it times square root of 4 times 3, right? So we can simplify that square root of 12 into square root of 4 times 3, which is square root of 4 times the square root of 3, right? We're looking for the highest perfect square that goes into that. And then square root of 4 is just 2. Okay. So now our square root of 12 becomes 2 times the square root of 3. Okay. Now we have what are called like radicals because they're the same thing inside the square root. Okay. Now what we're saying is we have 5 of these things, these square root of 3's, and we're taking away 2 of those square root of 3's. That's what that coefficient means. So all you have to do is take 5 minus 2 and multiply it times the square root of 3. So 5 minus 2 is 3, right? And then times the square root of 3. So if I have 5 of these being square root of 3's, and I take away 2 of those, then I have 3 of those. Okay? Because so we talk about like radicals, we're saying that's what those are, the square root of 3. Okay, now let's talk about multiplying radicals. So multiplication of radicals. Okay. We use the product rule for radicals that we already talked about. So remember, our product rule was this. Product of A times B in a radical is, break them out. Square root of A times B is square root of A times square root of B. Now we're going to use it backwards. Okay, so we're going to say square root of A times the square root of B is just square root of A times B. Okay, so you can say after the radicands are multiplied, when we do that, simplify the remaining radical when possible. Okay, so we're going to simplify once we get our answer. Okay, so let's look at an example here. Square root of 3 times square root of 27. Okay. Now we just multiply square root of 3 times 27, which is square root of 81, and that's actually one of our perfect squares because 9 squared is 81. 9 times 9 is 81, so that's one of our perfect squares. Okay. Second example, B, square root of 3 times the square root of 13. Okay, so we can put those together in one radical, just multiplying. 3 times 13 is 39. 39 does not have a perfect square in it, so we can just leave it like that. There's no perfect square that goes into 39. Okay. Square root of 6 times square root of 10 is square root of 6 times 10, okay, which is square root of 60. Now we want to look at the highest perfect square that goes into this, which is 4, right? 2 squared is 4. So 4 times 15 is 60. So that's square root of 4 times the square root of 15, which is just 4 square root of 4 is 2, so that's 2 times the square root of 15. Okay, so that's how we simplify our radicals, is that we find any perfect squares that go into this, okay, and take it out, right? And take square root, we get 2 for this case. Okay, now let's look at our quotient rule for radicals. Okay. Quotient rule for radicals says if you're taking a quotient in a radical, you can break it out separately. So square root of a divided by b is square root of a divided by square root of b. Okay. A and b, a has to be greater than or equal to 0, so we're not going to take square root of a negative. And then b has to be greater than 0. It can't be 0 because it's in the denominator, right? We can't divide by 0, so we would not have b would not allow to be 0. Okay. Now here's something that we have to be careful of. If you're taking square root of a minus b, you cannot break it out. Like you can't take square root of a minus square root of b, so we have to be careful of that. That does not work. Okay, but when you're dividing, and we're kind of looking at this backwards, if you're dividing inside a radical, you can break it out. Okay, let's rewrite that so it's in the right order. So really what we're saying here is this, just reading it backwards. Square root of a divided by b is square root of a divided by square root of b. Okay. Okay, so let's say we're looking at square root of 75 divided by square root of 3. Okay, we can put those together as square root of 75 divided by 3. Okay, which is 75 divided by 3 is 25, so that's just square root of 25, which is 5. So, you know, we can't normally take the square root of 75 and get a number that's not irrational, right? This will be, you know, we'll have an irrational number in it. And same with square root of 3, but if we take them together and take 75 divided by 3 in the square root, we get square root of 25, which is a perfect square. Okay, now we're going to talk about the concept of rationalizing our denominator. Okay. We rationalize our denominator. Denominator is rationalized when it has no radical expressions. In other words, we don't want radicals or square roots in our denominator. Okay. So in order to rationalize our denominator, what we're going to do is multiply both the numerator and the denominator, both parts of the fraction, by the square root of the number. Okay. That will result in the radicand in the denominator becoming a perfect square. In other words, it goes away. Okay. Then simplify the fractions when possible. So we want to eliminate our square root in the denominator by multiplying times the square root in the denominator on the top and the bottom. Okay, for example, let's look at 5 over square root of 2. We don't want that square root of 2 in the denominator. So what we do is if we multiply times the square root of 2, it becomes square root of 2 times 2, which is square root of 4, which is just 2. Okay. In fact, we could say this. Let's kind of write out this rule. Square root of a times the square root of a is just a. Right? Okay. So because it's the square root of a squared. Okay. So that we can recognize that. So square root of 2 times the square root of 2 is 2. Okay. So we're trying to get rid of that radical in the denominator. So we multiply times the square root of 2 on the top and bottom. Remember, we have to multiply the top and the bottom times the same thing with fractions, right? So this becomes 2 on the denominator, and then it's just 5 times the square root of 2 in the numerator. So 5 times the square root of 2 over 2. So this would be the simplified version of 5 over square root of 2. Okay, and what we're doing is we're rationalizing the denominator. We're making sure that it's a rational number, not an irrational. Because it's irrational, it would have still the square root. So we're trying to get rid of the square root in the denominator there. Okay, now let's talk about estimating square roots. So how do we figure out what a square root is without using a calculator? How do we estimate? Okay, so let's look at. We're going to look at a couple examples. We're going to use a ruler kind of as a guide. We'll look like square root of 7 and square root of 89. So what we can do is say, okay, we're trying to find the square root of 7. So let's look at perfect squares that are below 7 and above 7. Okay, in other words, we're going to try and sandwich 7 in between two perfect squares, and that would be 4 and 9. 2 squared is 4, 3 squared is 9. Okay. So what we can do then is take the square root of every part. And we know, 7 is between 4 and 9. So 4 is less than 7, which is less than 9. Okay. 7 is between 4 and 9. And then we just take the square root of every part. So we take the square root of 4, we know that's 2, right? We take the square root of 7, and we don't know what that is. And we take the square root of 9, which is 3. So we know that square root of 7 is between 2 and 3, okay? Now, since 7 is closer to 9 than it is to 4, then we're going to make square root of 7 closer to 3 than it is to 2. So we're going to put it somewhere around here, right? Maybe, between 2.5 and 3, okay? So the square root of 7 would be somewhere between 2.5 and 3 in our ruler, okay? Think of it like our number line, too. Okay, now let's do square root of 89, right? We're going to estimate that. So we start with 89, and we look at perfect squares below that, and just above that. So we know 9 squared is 81, right? 9 squared is 81, and 10 squared is 100. So 89 is between 81 and 100. So we're going to say 81, 89, 100. 81 is less than 89, which is less than 100. And then we're going to take the square root of all three parts. So square root of 81, square root of 89, square root of 100. Square root of 81 is 9. Square root of 89 is, we don't know yet. Square root of 100 is 10. So we know that the square root of 89 is going to be between 9 and 10. Okay. Now, since 89 is closer to 81 than it is to 100, we can say that the square root is probably going to be closer to 9 than it is to 10. So we'll probably put it somewhere over here, right? Put it somewhere close to 9. Okay. Between 9 and 9.5. So we're just estimating, but we'll say, maybe 9.3 or 9.2 or something like that. Okay, and if we use a calculator, scientific calculator, to show these, we're going to see that square root of 7 is about 2.65. It's between 2.5 and 3. And square root of 7 is about 9.43, which is between 9 and 9.5. Now, this does not mean exactly. Remember, our irrational numbers, like square root of 7 and square root of 89, which these are, the decimal keeps going, and it keeps going kind of in a seemingly random fashion. There's no pattern to it. There's no repeating pattern. So this is an estimate, which is why you use that squiggly equals. Okay, and same here, because we're only looking at 2 decimal places. Okay, and this one we're only looking at 2 decimal places as well. So these are approximations. So we're using scientific calculator to approximate our square roots because we only have so many decimal places. Even if we did 7 or 8 or 10, we're still approximating because we're not going to show all the decimals, right? Because the decimals go on forever for these irrational numbers. Okay, we'll look at some examples in class again and talk a little bit more about radicals and taking square roots.